Alright, this video has a modified Atwood machine where one mass is hanging and one mass is on an incline. Okay, so it looks kind of complicated. It is a challenging question, but we'll break it down into its pieces and we'll go from there. So for these questions, you're going to have some angle here. Okay, in this one, it is 20 degrees. So we want to know magnitude and direction of the acceleration of the system if it's inclined. For this one, we're going to assume there's no friction, but we will talk about where friction would go if there was some. So we're going to follow our little list here again. Find F net two different ways for the system. So first one is I have two masses, so my net force will be those two masses added together times the acceleration of the system. I'm going to say this is M1, this is M2. So step one is done. Step two, find another equation for net force. Okay. Well, I know I'm going to have Fg1 pulling down here, and mass 1 is 5 kilograms, mass 2 is 3 kilograms, so I know it's going to be accelerating in this counterclockwise direction. But what I want to know here is, yes, there's Fg1 here, but how much force is there pulling down this way, right? Because that's going to be the force I need to subtract out. Well, back to our inclines lesson, this is going to be Fg2, and I can break that up into a perpendicular component and a parallel component. So I'm going to call this one here my perpendicular component, and this is going to be my parallel. So the force that's counteracting is going to be Fg2 parallel. Okay? Fg2 parallel. Now, looking at our little incline here, that's going to be 90 degrees, and this here is going to be my theta. Now, if you haven't seen the inclines lesson, go back, watch that, because I'm going to be leaning on inclines knowledge here in order to do this. So here, this bottom part is my Fg parallel, and if you remember from my inclines lesson, my parallel component is going to be my force of gravity times the sine of the angle. The sine of the angle. And if we look here, I have my angle here, and this is my opposite side, so that's why I'm using sine. So I'm going to be using that in just a second. Again, this is Fg2 because it's on mass 2. Okay, so I got my second net force. Now I'm going to expand this one. Fg1, well, that's mass 1 times g. And Fg2, the parallel component, is Fg2, which is mass 2 times g as well, but times the sine of the angle. And from this, I can actually factor out a g. So I'm going to have mass 1 minus mass 2 sine theta all times my g. And these are my two net force equations that I'm going to make equal to each other. So let's see, make the two F net equations equal to each other. So that's what I'm doing now. And then I'm going to solve for acceleration. So I have mass 1 plus mass 2 times my acceleration is equal to mass 1 minus mass 2 times sine of theta times g. I divide both sides by m1 plus m2, and I'll get my acceleration m1 minus m2 sine theta, all divided by m1 plus m2. Now, memorizing this equation is not going to work, unless you have an amazing memory, but understanding how to get it, that is possible. Okay, so all of these symbols look kind of confusing, but if you're staying with me, if you've been doing the other lessons too, hopefully you would actually be able to kind of derive this on your own. Okay, so this is the equation that we can use when we have an Atwood machine, one hanging mass, and one on an incline. So let's take a look here. I'm going to solve it over here, so I'm going to sub everything in. My acceleration is going to be 5 kilograms minus 3 kilograms times the sine of 20 degrees. And notice sine of 20 degrees is just a unitless multiplier again. So that is going to result in none of my units actually changing here. And when I do this, I'll get 5 kilograms minus 1.03 kilograms after I multiply it by that sine over 8 kilograms. And that's all multiplied by my acceleration due to gravity. And once I do all of that, my acceleration is going to be like exactly half. It's 0.5 times g. So it's exactly 50% of what the acceleration due to gravity is. So that's 4.9 meters per second squared. And that is all going counterclockwise. Okay. So this is my acceleration of the system. Right there. Okay, nice work. We got that. Next one. Draw a free body diagram for each mass individually. Okay, so I'm going to be doing that down here. Again, I'll have mass 1 and mass 2. I'm going to give myself a little bit more space for mass 2 just because I have it. Mass 2. Okay, mass 1 is hanging. So I got the force of gravity on mass 1, and I have a tension force counteracting that. Now again, I got my net force is going to be mass 1 times g, and also another way of writing my net force is going to be my force of gravity 1 minus tension. I rearrange this one for tension, and when I do that, I'm going to get my force of gravity on 1 minus my net force. Now I'm doing some algebra steps that are kind of quick. So what I did is I added tension to both sides, then I subtracted net force from both sides. And when I sub in everything, Fg1, well that's m1 times g minus F net, I'm getting that from here, I'm subbing that in, is m1 times acceleration. Oops, I made a mistake earlier. That should be acceleration. And when I factor out my m1, I get g minus a again. And remember, this was my tension equation for something that was falling. Okay? And when I work this out, I'm not going to do the step where I write everything out, but I have done this, and I get 24.5 newtons, 24.5 newtons acting upwards. Now I'm actually going to round this up to 25 because my work revealed my second way of solving for tension a little different than that, but it's just rounding issues. So if I make it less sig figs, it'll match. So roughly 25 newtons acting upwards. Now mass 2 is a little more complicated. It's an incline. Okay, it's an incline, so I have to draw a free body diagram using my incline's skills. So I'm going to draw a perpendicular and a parallel axis. Okay, that's my perpendicular, that's my parallel. Now I have the force of gravity on 2 pulling down, and I got to break this up into its components. Okay, I've got my force of gravity 2 perpendicular and my force of gravity 2 parallel. And my angle here is 20 degrees. Now I've also got a normal force. Okay, a normal force here, and my normal force is going to match my perpendicular components, and I've got a tension force. Tension force acting up the incline. That's where my tension is. And tension is going to be greater than my force, the parallel. So tension is greater than my my parallel component. So let's set this up and solve this one. So again, my net force for this is going to be my mass 2 times however it's accelerating. And then my other net force is going to be tension minus Fg2 parallel. And when I rearrange that for tension, I'm going to get net force plus Fg2 parallel. So now I just sub in my stuff. I know F net is m2 times A, and I know Fg2 parallel is m2 times G times the sine of my angle. And here, when I sub out my mass, or I factor out my mass, I'm going to get the acceleration of the system plus G times the sine of my angle. And this is an equation that you can use to solve for tension on an inclined Atwood machine. Again, Mr. Smith's worksheet, thank you so much. Little shout out to him. And now if we sub in all of our numbers, so here if I do this one properly, I'll sub in my numbers. 3 kilograms times the acceleration of the system was 4.9 plus 9.8 times the sine of 20 degrees. I get my tension is going to be 24.8, or when I round that up, I'd get 25 newtons, and this is going to be up the incline. Okay, again, notice your tensions should match. Okay, students ask me, do you have to calculate it both ways? You don't technically, but this is kind of nice because you can check if you did it right, right? If your tensions are close or if they match, then you know, hey, I must have done this question correctly. Okay, let's talk over these equations a little bit. Take a look here at our big equation, okay? Let's talk this over. If our angle was 0, okay, if our angle was completely 0, that would mean, well, sine of 0 is 0, that would take this term out of there entirely. Okay, and if we did that, this is the exact same equation that we had on the previous video, where it was just a horizontal surface. Okay, well that makes sense. Let's say the angle was 90 degrees, so it was exactly like two hanging masses essentially. Well, then the sine of 90 is 1. That would go away. And that was the equation we had on our first example of the pulley with two masses over top of each other. So kind of interesting how this equation is kind of just a combination of our last two. Alright, now the last thing that we wanted to talk about is, what if you get a question like this and there is some friction? Where is that going to go? Well, friction would be my net force. It's going to go in this equation here. My net force is going to be Fg1 minus the parallel force, and then here I would still have minus my force of friction. Okay, that's if the object is moving this way, then friction is going to be going this way. If the object is going the other direction, then friction would be acting in the opposite side. But here, remember from my friction rules, or my friction equation, it's going to be my coefficient mu times the normal force. And on inclines, my normal force is equal to my Fg parallel, or perpendicular. So that's another little thing to note there. Some of the questions on the worksheets are slightly more complicated than this because they do have friction, but take your time, go through the ones without friction first and solve them. Really, the part that's going to be changing depending if there is friction or not is this part of the equation here. So this part of the equation here, your F net, the second way that you set up your net force equation is where friction would come in, and this is where things would change. So when you set up your second net force equation, draw the best free body diagram you can if you're stuck, and just try to think, what are all the forces acting on this object, and see which direction is it accelerating. That'll also kind of give you a hint as to which direction the net force is heading. So that's it for this video. Work hard, and I'll see you in the next one.